Let's begin with a brief introduction from Dr. Panagiotis Michalis, Project Manager of THETIDA and Senior Researcher at ICCS at our team, who will set the stage for today's discussion. Mr. Michalis, Dr. Michalis, the floor is yours.
Thank you very much, Dimitri, for the introduction. I suppose that the introduction of the speakers will be made after my short presentation of the project. So I continue to the next slide. Hello, everyone, also on my behalf. I'm Panos Michalis. I'm a Senior Researcher and Project Manager at the Institute of Communications and Computer Systems, mainly coordinating the activities of THETIDA project. So the aim of this very short presentation is to provide you an overview of THETIDA project, and then we will give the floor to our guests and invited speakers. So THETIDA, the main aim is to develop, test and validate an integrated underwater and coastal heritage risk management and protection system using evidence-based monitoring frameworks, innovative underwater and coastal tools and instruments that are developed as part of the project, but also employing participatory processes by linking social innovation with cutting-edge technologies. We are a consortium which consists of 8 participating countries, 17 partners and 7 pilot sites. We have 5 SMEs on board, 8 research institutes and 4 NGOs and public organizations. Claudio, can you hear me? Or anyone, can you hear me, everyone?
Online you can be heard very well, but I don't know in the classroom. Claudio?
Claudio, can you hear us in the classroom? Probably no. Dimitri, can you hear me?
Yes, I can hear you loud and clear. So yes, and also, yes, all the online participants. Can you confirm from Professor Rufolo's classroom if you can hear us?
Now yes.
Okay.
Yeah.
Perfect.
Yes. I can hear you, yes.
Thank you, yeah. Okay, Panos, you can continue.
Okay, thank you. So we have a duration of 42 months. We started at May 2023, so we're now have entered the final year of the project, and we have received a funding of approximately 4 million euros. Dimitri, if you can mute the participants, because I hear some background voices. Thank you. A quick overview of the pilot sites. So we have 7 pilot sites on board. We have 4 underwater sites, which is the Gainara Island in Albenga in Italy, is the Equa World War II steel shipwreck in La Spezia, also in Italy. We have in Algarve in Portugal the consolidated B-24 Liberator, which is an airplane wreck which is located at the bottom of the ocean. And we also have the 4th underwater pilot site at Niskia shipwreck, which is in Cyprus and is an Ottoman shipwreck from the Ottoman era. And we have 3 coastal sites, Lake Iezet in Netherlands, the Hjortham coal cableway station in Svalbard, Norway, and the Castle of Mykonos in Greece. So we have coastal threats like erosion, heat, drought, earthquake, anthropogenic influence, flooding, soil subsidence and deformation, seepage, but also we have underwater threats like temperature in different depths, water pollution, acidification, human and dust activities, falling, overblooming, earthquake, currents. The methodology that we approach is that we employ different types of technologies like remote sensing to assess coastal erosion, deformations on coastal sites, but also to feed with inputs and information to develop the ocean forecasting system and the climatological and geohazards maps, which are being developed and deployed in specific pilots. On ground, on water, actually, we have the surface vessel sensors, which are boat sensors that are deployed from boats and are being used as crowdsourcing and mobilizing relevant communities like fishers or Coast Guard. We have a smart buoy which is being deployed at Nisja pilot site and provides information about wave characteristics, but also environmental parameters at the site. But also we have seabed and wearable sensors. So seabed sensors permanently based at the location and the depth of the shipwrecks, but also wearable sensors that are being utilized by divers in order to obtain measurements of environmental parameters at certain depths. And we also have an autonomous underwater vehicle which has been developed and currently applied with different types of sensing technology like side-scan sonar, hyperspectral camera, etc. On the coastal side, we have smart tags, which measure micro cracks, but also temperature variations on coastal sites, micro weather stations applied at Mykonos pilot site, but also we have developed a crowdsourcing mobile application in order to give the opportunity to citizens to make reportings about potential hazards occurring at the sites, but also providing them with overview and 3D documentation of the pilot sites in order to make them more aware of the risks. So all these are being used together with the material analysis that will be presented later on in the webinar today, are being used to model risks, to predict, but also to visualize. And this visualization is being fed back through living labs and citizen tools to raise awareness, evaluation, and engagement for resilient and climate-neutral cultural heritage. So the main objectives is to safeguard and protect the Europe coastals and underwater heritage by exploiting cutting-edge monitoring technologies. But also part of our activities is to promote, test, and demonstrate innovative and sustainable modeling tools and a decision support system to support relevant heritage stakeholders in terms of risk monitoring, but also of taking timely decisions. All these are happening through the engagement in participatory and inclusive data acquisition through citizen science and living lab methodologies, and all the developments of THETIDA are validated currently during the last year and demonstrated in the 7 pilot sites that were presented earlier. Apart from that, we're also leading and participating in the EU Green Cluster on Cultural Heritage, which consists of 4 different EU active projects. And the main aim is to bring together the different actors from the projects, from practice, research, and policy, to promote the development and adoption of advanced tools, but also share and exchange insights and best practices that developed as part of the project, and identify synergies and propose integrated feedback recommendations to policymakers in the European Commission and beyond through a white paper that will be published by the end of the year. This is the consortium of THETIDA project. As I mentioned, it consists of 7 big partners, and more or less that's it from my side. Dimitri, I suggest that we go back to the slide that you introduced the speakers, and then we provide the floor to each speaker. Please.
Yeah. Thank you, Panos, for that overview. And as you have already seen, you can find some links for our social media profiles, YouTube channel, and our website on the chat. You can follow us just to be updated about what our project does. And we do a lot of nice and interesting things. So let's now turn to our speakers for today. We have together 3 highly respected researchers, professors, who bring a wealth of expertise in geosciences, conservation science, and heritage preservation. From the left, To the right, you can see here on your screen that we have Professor Claudio Mazzoli. He's an associate professor at the University of Padova at the Department of Geosciences. Professor Mazzoli will present on the recession rate of carbonate rocks used in cultural heritage and how experiments can help refine current models for understanding stone decay. And then we will have the honor to listen to Professor Maritain, Lara Maritain. She will give a very insightful and methodical approach to understanding submerged ceramic heritage. And of course, Professor Lara Maritain is also from the Department of Geoscience and University of Padova, UniPD, UniPD, the University of Padova is also a partner on our project. And last but not least, we have our final speaker, Professor Silvestro Ruffolo from the University of Calabria, that will elaborate and explore the biodeterioration of submerged cultural heritage and present sustainable approaches to conservation in marine environments. So, getting back to our first speaker, I would like to give the floor and call Claudio to share his screen. And Claudio, once again, thanks not only for presenting today, but for coordinating also with the other two professors. Thank you very much, and we cannot wait to hear you.
Okay, good morning, everyone. Let's see. I don't see the screen that I was sharing before. Okay.
Perfect. We can see your screen. You can start. Yeah, thank you.
Okay, but I cannot see it myself now. Okay. Okay, now everything seems work fine. Okay, good morning. So right. So that's what I will talk about this morning. Recession rate of carbonate rocks used in cultural heritage. This is a flowchart of my presentation. We will start with a few basic concepts on stone deterioration and why we specifically care about stone deterioration in cultural heritage, and specifically why on carbonate rocks, and then we will go through modeling surface recession of carbonate rocks, and I will then show the main limitations of present models through a series of results from experiments, and then we will go to some concluding remarks. So stone deterioration, what it is well, first we have to say that it's a natural and inevitable process that affects all rocks, but at different rates. And it is influenced and determined by different parameters, which are environmental parameters like temperature, relative humidity, wind, rainfall, solar radiation, but also pollutants, and also depends on rock properties like mineral composition, texture, porosity, and pore size distribution, fracture networks. That means that if we want to know what is the deterioration rate of a rock, we need to know all these parameters and know how these parameters interact and determine for that specific rock the deterioration rate. This deterioration takes place through different mechanisms, which can be physical, chemical, biological, but also human-driven. Physical are normally related to changes on environmental parameters like temperature, relative humidity, or influenced by the presence and the crystallization of salt, or ice, or also abrasion, for example. It's a physical aspect, but there are also chemical mechanisms related to dissolution, hydrolysis, oxidation, acid attack. And in deterioration, also the life word, it's important because biological mechanisms are also relevant for deterioration related to colonization of bacteria, fungi, lichens, algae, or higher plants. And of course, also human-driven, especially if we are dealing with cultural heritage like vandalism, mechanical stresses related to the use of stones in architectural elements, or also relating to restoration using incompatible repairs or materials. So stone deterioration is a complex phenomenon involving all these mechanisms, normally all together. So why we care about stone deterioration in cultural heritage? Well, first, because of the cultural significance. Stone carry history, identity, craftsmanship, and artistic value. Therefore, deterioration causes irreversible loss of cultural meaning, but also scientific and historical information may be lost because surface, tool marks, inscriptions, pigments, and construction details can degrade and disappear, and the loss of all these aspects mean loss of information and about past cultures and building techniques, and therefore we lose material for studying and understanding our past. But also structural stability and safety can be in danger because progressive decay compromises mechanical integrity, and with the risk of collapse of monuments and adjacent structures. And decay also have important economic and impact on tourism, for example, because heritage sites support local economies, and deterioration leads to expensive intervention and loss of income. Just to give an example of what this means, in this slide, you can see on the left an image of a gypsum cast of the Trajan column in Rome, and the cast is also preserved at the Museum of the Roman Civilization in Rome. And on the right, this cast was built in the second half of the 19th century, and so reproduced the situation of the Trajan column at that time. On the right, you can see an image taken in 2019, so that means 150 years more or less after, and it's clear the loss of details, the loss of information that is well beyond just, the loss of material. He says that you don't read as clearly as you could just 150 years ago. So stone deterioration in cultural heritage, it's of our concern even more than just stone deterioration in general. And we have legal and ethical responsibilities. Protection mandates are established by international conventions like UNESCO, for example, and it's an ethical duty to pass cultural heritage to future generations. But these this type of values are changed with time, and so it was not always like that. So in the past, historically, the focus was mainly on functionality, and so there was a continuous repair and replacement of stones that broke up and or deteriorated or was not functional anymore. But modern conservation focuses on original materials, and since 19th, 20th centuries, heritage values shifted towards authenticity, integrity, and preservation of original fabric, with the idea that each stone remains unique, historical, artistic, and scientific information, brings historical, artistic, and scientific information, and therefore what we have to do is to use minimal intervention and reversibility in the in type of intervention on cultural heritage. And conservation principles are also listed and highlighted in different charters, for example, Athens and Venice charters, which establish the importance of regular and permanent maintenance, respect of historic and artistic work of the past, acceptance of modern materials when appropriate, and also the protection of the surroundings, recognizing settings, but also that conservation aims to preserve and reveal heritage value, and that restoration must stop where conjecture begins, and new additions must be distinguishable and reversible, and that restoration requires scientific study and full documentation. So a radical change in the view of conservation. So why specifically on carbonate rocks? Of course, deterioration is important for any rock type, but specifically on carbonate rocks. The first is that they have been and are widely used for different reasons. The first is workability. So carbonate rocks are softer, and so it's easier to quarry and to carve. So they are specifically useful, suitable for sculptures and architectural decoration, and their availability. They are abundant near many historical centers, and also for their aesthetic qualities. Normally they are white or light colored, so they are nice looking, or there are many different colors possible, and so they have different ornamental textures and appreciated features. But on the other hand, they are more vulnerable than, or normally they are more vulnerable than silicate rocks, and for different reasons. The first is that they have higher solubility, and they are sensitive to acid attack, and therefore under the dissolving action of rain, they undergo faster deterioration, and they are susceptible to salt crystallization. But this is valid for many different rocks, of course. But because this is often related also to porosity, they can be porosity can be quite high, and therefore often they are quite vulnerable to salt attack. They also have lower mechanical properties and abrasion resistance that many silicate rocks, and they may be vulnerable under thermal microcracking, especially in marbles, because often in marbles calcite is oriented, and especially in coarse-grained marbles. So, of course, okay, deterioration is important. Assessing deterioration is important, but it's important to model deterioration rate, because we need to know what is the rate of deterioration, and this for a risk assessment and prioritizing conservation actions, and with proper models we can provide future scenarios, for example, under climate change, and in this way supporting cost planning and maintenance scheduling. Decay of carbonate rocks normally is expressed as surface recession, and there are for example, microns per year, and there are different equations used. One of the most used one is the Lippert equation, which is written here below. Apart from the numbers, what I want to highlight is that is made of three different terms. So the first is the karst effect, which is the dissolution rate of calcite under unpolluted conditions. So in a normal, just due to the natural effects in unpolluted water. And there is a second term which accounts for rain acidity, which is the wet deposition, and the third one, which is the dry deposition, which accounts for pollutants present in the atmosphere and their deposition velocity. And based on this equation, and considering future scenarios for climate change in Europe, there are models of the change of surface recession, and so accounting for future climate scenarios. And this type of models provide a tool for example, for intervention and for establishing which are the most vulnerable places, and consequently the cultural heritage, which is after a major threat. Okay, so this is based, of course, it depends very much on how reliable the equations that are used are, and how precise are the forecast, the climate change future scenarios, and of course these introduce very large uncertainties. The same, this is here the different colors represent the yearly recession, surface recession. So if it's red or dark red, that means maybe 25 up to 30 or more microns per year. If it's bluish, that means between 0 and 5. So not that much, but still, I mean, with time you accumulate recession. This type of models can be represented even in a different way. So, for example, here on the left, you have a baseline representing the recession rate in the period 1961-1990. And on the right, the difference in the far future, so it's between 2070, 2099, the difference respect to the baseline. So it tells you whether you have intensified deterioration towards the red, or more or less the same, gray, or towards the blue if you have a slowing rate to the baseline. This is not the only equation that is available in the literature. There are many equations linking pollutants and weather climate conditions. Here is a list. All of them express stone loss in terms of microns of recession per meter of rain per year. And apart from, again, going through the equations, what I want to show is that what are the parameters that all these equations consider. One is acidity term, so it's a function of water pH, rainfall, so how much is raining, the deposition velocity of pollutants, the concentration of pollutant in the atmosphere, temperature. Very few equations consider also temperature, which is a parameter that is important because solubility of carbonate changes very much with temperature, so it should be considered. But the problem is that it's not air temperature, it's water temperature in contact with the rock. And so it's a bit tricky to have time series of data of this parameter to be able to include this parameter into an equation and to be able to use this, okay? And time of wetting is another important parameter. So it's clear from these parameters that there are critical limitations of these equations, which introduce huge errors in the estimate of recession. That means what can we really use them for in terms of future projection and in intervention strategies. So these clearly the limitations relates to important missing variables like petrographic properties, carbonate mineralogy, for example, whether dolomite or calcite grain size, porosity, pore size distribution, but also color, which affects solar absorption. And microclimate effects, so solar exposure, facade orientation, wetting, drying cycles, freeze, thaw cycles at the micro scale. So all these aspects are not included and in these equations, and they are is really relevant. Here, for example, on the right, you see 3 images of 3 different carbonate rocks under the microscope, and you see that there are significant differences in the textural properties, like micrite, which is a very fine-grained calcite in some parts, but some others are bioclast with a fiber structure, or areas with a sphaeritic coarse-grained calcite. So all these different elements have a very different dissolution rate. So of course you have to account for them into the equations if you want to reliably have an estimate of the recession rate. Or here in this middle one, where you have dolomite and micrite, or here in the bottom one, where you have a mudstone with a very fine-grained micrite and fractures filled in with sphaeritic calcite. So experimental evidences of the importance of the microstructural and mineralogical effects on recession. Here on the images that you see on the right side of the slide, the two on the left represent a map of a 3 by 3 millimeters area on two silicate stones, and on the right the same area, exactly the same area after 240 aging cycles. And what you see clearly is that you have a significant change in surface roughness, but also that recession, it's very different depending on the mineralogy. So the dolomite here, it's basically at the same height as it was at time zero, and but calcite, you have a significant loss of material where there is calcite, but also that depending on the grain size, so the micritic parts here, recession is much higher than in the parts where you have the sphaeritic components of the coarse grained calcite. And you can see even better these evidence on this graph, where you have the grain side here on this side and against the recession. So you have the recession as a function of grain size, and it is clear that there is a correlation between the two, and of course that also there is an important effect of water pH. So the two lines, the orange one and the blue one, represent two trends obtained from two different waters used during the experiments. So that means that grain size strongly controls recession rate. That means you cannot avoid considering also this parameter into the equations. This experiment, it's a bit different from the previous one. It's considering exposing the stones to different microclimate conditions by locating the same set of stones from different sides of a cube, and in such a way that some are exposed to the south, some are horizontal, and from the other side that you don't see here, they are exposed to the north. And the environmental parameters are acquired from a weather station, and surface temperature and relative humidity. It's has been measured for each of the slabs through a specific acquiring system. And such cubes have been located in three different places to obtain also information about the influence of different environmental conditions. So what can we see from the measurements that we made on these experiments? Here you see in yellow and in red the temperature variation for two different rocks, both exposed to the south. And in the thin blue line and the red thin red line represent the variation of air temperature, and the thick yellow line and the red line represent the temperature variation measured on the surface of the stone. So what is clear from here is that maximum temperature on the light colored rock is lower than the maximum temperature that you measure on the dark rock. So meaning color influences albedo and therefore surface temperature and therefore thermal cycles. But if we take the same dark rock and we compare the temperature pattern of the same rock exposed to the south in green to the one exposed to the north in gray, we see that there is also on the same stone a great difference influenced by the orientation. So again, you cannot avoid considering the exposition of the stone if you want to determine precisely or what is the deterioration rate of that stone. And let's see here what we actually measured on these stones. So, for example, this is a map obtained with an optical profilometer, and the different colors represent the different in elevation of each point respect to a stainless steel marker, which is the gray part top left of the images, and the red circle represent a micrite element, and so the top image is the topographic map used as a baseline measured before the beginning of the experiment, and the bottom one is exactly the same surface after 1 year. So what you can see here is that the difference is in elevation of the red spot. For example, in 1 year, it's 19 microns, and in yellow, the element is a bioclast, and the net recession of that point is 16 microns. So there is a difference depending on the textural characteristics of the different elements. And from these type of maps, you can obtain the bulk average recession. And on the right-hand side, on the top, you can see that for example, the recession measured for the this Costozza stone, which is a common stone used around here in Padua, in 1 year, it's you see almost 6 microns for the slab exposed to the south, to the north, while the horizontal one of the same stone, it's almost 3 times. And also the one exposed to the south is the bar on the right. It's it's significantly higher than the one exposed to the north. And in the bottom diagram, you see that there are significant differences in the recession depending on the textural element that you are considering, whether it's a micrite in orange or a bioclast in blue or a sporitic calcite, so a coarse-grained calcite in gray. So that means we have to consider orientation if we want to determine exactly what is the recession rate of a carbonate stone exposed to the specific environmental conditions. Interesting data you can also obtain from war cemeteries like the one of the Commonwealth, because here you have large numbers of headstones of the same material exposed to the same conditions in one cemetery, or to different environmental conditions from different war cemeteries in different climate regions. And you can observe, measure, have statistical significance of the measurements because you have many slabs. You know when they've been starting to be exposed, and you can obtain time series of environmental parameters from that location. So these are important data that can be used to calibrate recession equations. So as a concluding remark, I'd like to say that, well, we are far from having reliable equations of recession of carbonate rocks. We have many different data from the literature, from experiments, from outdoor experiments, and from direct measurements of recession data. These data need to be crossed and correlated with microclimate conditions and not just, the standard environmental parameters, and considering also petrographic and textural properties to obtain robust and reliable models to predict stone recession. And but one important aspect that we have to consider is that recession rate is not the whole story, because with recession you have loss of details, and therefore means loss of legibility and value, and heritage significance depends on the visibility of these details. And the other aspect is that geometry. It's important because curvature, orientation, and surface roughness also influence the recession rate. And so you may have differential recession depending on the curvature, for example, of the surface. And that means also all these parameters should be calibrated and the influence incorporated into the models. And so there is the need for damage functions relating recession to cultural value. And here it's just a sequence of images that I generated with the AI, but just to show what I mean for loss of legibility, if it was not clear enough from the example of the Trajan tower, of course. And so deterioration, it's of course a global challenge, but not only on land, also underwater, because bioerosion can be very aggressive, and dissolution mechanisms different from rainwater. And of course, there is also the effect of hydrodynamics and sediments in abrading and wearing materials. And that means basically that there are different deterioration mechanisms than on land taking place underwater, and in which we have limited long-term data, and models are still poorly developed. And with this, I concluded my presentation. I thank you for your attention.
Thank you, Claudio. Thank you, Professor Mazzoli, for that fascinating and technically rich presentation, I would say. And now, without further ado, we move to Professor Lara Maritan, also from the same department as Professor Mazzoli. Lara, the floor is yours. You can walk us through the mineralogical and chemical alterations that ceramics undergo when submerged for long periods. The floor is yours.
Can you see the screen? Yes?
Yes, we can see the screen.
Great.
So we have to say that this topic is quite a wide topic. She's talking about alteration of ceramic comprising different aspects. So today we try to focus on what is happening in ceramics, which experience a more or less long period in underwater environments, under obviously different mineralogical and chemical point of view. But before doing that, let's make some an introduction about the alteration of ceramics and why it is so important to study it, and which are the evidence that tell us that ceramics underwent alteration. So the alteration happened because the ceramic, which is a porous material, interacted with the post-depositional environment, and especially, and we will see there are some parameters which will be involved. And the main feature that we recognize on microscopic scale is that the color variation of some of the parts, which are related to chemical, mineralogical, and sometimes macrostructural changes in the original material. What is important to understand that the ceramic underwent alteration is so important because we use a ceramic for trace provenance and to determine the ancient production technology. So if we don't understand that a ceramic underwent important alteration during the barrier period, we can misinterpret the data. We can not find the place where the material can come from, or we can, for instance, determine wrong firing temperature or wrong oxidizing condition of the firing. So this is just an example of a material produced, a same type of material, in this case, a ceramic like a red slipware, occur with different colors according to the place in which it was deposited, according to the post-expositional environment it experienced. So the chemical and physical condition of the post-expositional environments are the those mainly affecting the stability of the minerals, and they are represented by the pH, so the acidity or basicity of the circulating fluid, the EH, which represent the oxidation potential, the chemical composition of the circulating fluids, and we see that can be different, the temperature, obviously, the saturation of the circulating fluids, as well as possible biological agents, right? So all of them occur in a different entity to the alteration of the ceramics, and they are strongly related, obviously, to the type of environment. So talking about a terrestrial environment is very different from talking about a marine environment or underwater environment. But obviously, there are other factors affecting the alteration of ceramics. which depends also on the other materials present in the archaeological site, like food remains, bones, metal, wood, fibers, and many, many others. Is right. So the main thing is that since the ceramic material is mainly composed of minerals, and we have also a little bit of amorphous material, what is important for us is to understand the stability of these minerals in terms especially of pH and EH, because most of the stability is related, and for the other factor may affect mainly these parameters, these physical parameters and chemical parameters. So therefore, if I have a mineral phase which formed into the ceramic, or it is a relic of the clay used, it may be undergo dissolution or to transform into something else, because the field in which it was originally formed is not available anymore in the environment that the material experienced during the burial or during the post-positional period. So, for instance, a decrease in pH determines instability and can determine dissolution, for instance, okay? Or transformation to another mineral phase. So let's say that it's very, very important to understand the physical condition of the environments. And in this case, we can divide roughly the post-positional environments into three big families: the terrestrial, the marine, and the transitional. So the terrestrial, we have a variation in temperature and humidity. And we have circulation of fluid, which can change a lot depending on the site. For instance, if we have a material buried for a long period here, for instance, in northern Italy, it's a wet environment, very, very humid, but it has also some seasonal changes, very different from a situation in which, for instance, we are in Egypt, which is a very, very dry environment, very, very little fluid circulating. But obviously there we have also the presence of salts, for instance. I make things simple, obviously, because they can be very complicated. Marine environment, talking about underwater environments, the water solutions are very rich in solid ions like chlorine, sulfate, sodium, potassium, calcium, and magnesium. We have normally a high salinity. It is an alkaline environment, and normally it has positive to negative EH depending on the depth and depending if the material is buried under some deposits in the sand, for instance, or in the clay material, or buried under other archaeological materials. So the material normally are always in contact with water. So it means that all the porosity is always saturated in water, right? Transitional environment are normally, they are characterized by salt water, the salinity is lower, and they can have a variable pH and EH. But today, obviously, we will focus on marine environments, and we will see what is happening during the burial period of a ceramic. So let's see the type of a transformation which can occur in a ceramic after the abandonment. We can have precipitation of secondary phases from water solutions. We can have mineral dissolution, which is just the opposite. We can have transformation of pristine minerals and amorphous phases into new mineral phases. We can have chemical leaching and enrichment. So these are the main transformation which can take place into the ceramics. So they can affect the components of ceramics, like the inclusions and the micromass. Here I reported a sketch, obviously, of a thin section. And then we can have also that our transformation can take place into porosity, which are empty spaces where new mineral phases can precipitate, or as well on the coating, which can be of different type. So let's see some example of precipitation of secondary phases. Obviously, I'm reporting precipitation of secondary phases into ceramics from underwater sites, right? I'm not focusing on ceramic from terrestrial sites today. So precipitation of secondary phases, they can occur at surface as incrustation. And here we have some example reported at the scanning electron microscope. We can see here some sections, some cuts of this biomineralization, and here as well. And in form of calcite and or aragonite. It depends on the type of organism which precipitated this incrustation. And these are some examples of what we see macroscopically. Obviously, the incrustation are very evident since first macroscopic observation. They can have a different color, and it depends a lot on the organism which determine them. But secondary phases can also precipitate into open pores inside the pot shelf, partially filling or completely filling the porosity, giving structure like a gel-like ones. So these are some examples of calcite precipitation inside the porosity. We can see, for instance, here, a big bags completely filled by secondary calcite. Always, I'm showing you always images under the scanning electron microscope, which are very good because they allow us to go to very high resolution, as well as coupling also a chemical microanalysis. Or like in this case, that the calcite form a gel-like structure. And we don't see the pointer in the class, sorry, I apologize for that, but great. So it's like a gel-like structure. But obviously, if we look at cut of ceramic in starting from the outside to the inside, we can see that sometimes we have that the secondary phases reach a certain depth into the ceramic, not involving all the material.
I think we have lost connection. Does anyone else face the same problem?
I think just Lara is frozen.
Yeah. Yeah. Lara,
Okay.
you were frozen for a couple of seconds, so now I think you are back with us. Can you hear us?
And
yeah.
Yes. And where did you lose me? At
Just
which
10
point?
seconds ago. At this point,
10
at this
seconds
slide.
ago.
Yeah.
So this slide was fine. This one, beginning of this one, probably.
Yeah. When you started this one, after 10 seconds, we lost you, so you can take it from this part.
Right. So we are talking about the precipitation of some mineral phases. A very common one is calcite. Calcite, which normally precipitate for pH exceeding 7, 8. And normally in underwater environment, this calcite is rich in magnesium. It is a magnesium calcite. It's not just calcite, but it's often rich in magnesium, right? And it can completely fill porosity like this large void, or it can form a geode-like structure, so partially filling the porosity. It can also permeate tiny pores that are, let's say, in the size of nanometers or just few micrometers. So the general effect that you can see is something like this, in which this whiter part, which is represented obviously by minerals having an average atomic number higher than the one surrounded, is represented by secondary calcite feeling the little porosity. And this happened, for instance, also here, in which you have that this lighter part is affecting only part of the ceramic material, not reaching the core of the ceramic body. But let's say precipitating little by little from the outermost surface to the inner, but at certain point stopping. Why is this happening? Because often it is created a sort of barrier in which the fluid precipitates the secondary calcite, but then the fluid are not rich anymore in this ion, so they do not precipitate calcite in the inner part. Right. We can detect this obviously also under a diffraction, on the diffraction point of view. So, and for instance, here there's an example of ceramic taken from the same type of material. They are amphoras, and some of them were found in land and in the production sites, and others were discovered in a cargo, which experienced almost, let's say, 18 centuries in underwater environments. And we can clearly see that in the materials which stay long in underwater, there's a crystallization of calcite that is not present in the one that we have from the land. So we compare the same material from two different situations, but obviously they differ in mineralogy, and this secondary calcite precipitated underwater. Another phase that you can meet during the analysis of materials from underwater sites is pyrite, which can form from different mechanisms. It's a very complex crystallization process, and it depends a lot on the environment, especially, let's say, on the quantity of sulfurs that we have in the environment, especially. We can have pyrite forming rhomboidal aggregates, which obviously record very high sulfide concentration, or as euhedral crystals, which record low sulfide concentration. Depends a lot. The shape reflect the concentration of these compounds. So provide us information also on the type of environment. Here are some examples, other example taken at high resolution scanning electron microscopy, in which we see that the rhomboidal aggregates can be also very tiny. So the crystals are very tiny, lower in size than a micron. And here a more detailed image in which we clearly see this rhomboidal form of very, very little crystals of pyrite. So, great. Another type of secondary phase that can form is, for instance, jarosite. This mineral phase actually did not form for only simple precipitation, but it derived from a transformation of a pristine phase into a new mineral phase, right? So we have normally a partial dissolution or reaction with a subsequent transformation into a new mineral phase. These are very complicated processes. What I'm telling you is that it's not simply happening a precipitation into porosity, but what is happening is a transformation of a mineral into something else, into a new mineral phase. And this is the case, for instance, of jarosite, which form in salted water for transformation of pyrite into acidic condition and for reaction with the sodium ions contained into the seawater. It's very complex, and what you can get is these are very, very nice crystals observed under the scanning electron microscope, which form like they look like roses, and they are thousands and thousands of crystals. But these crystals are very important because they actually turn the ceramic, which was originally red, into a ceramic material which become macroscopically yellow. So the material can lose the color, change completely, and so sometimes it determines misclassification of the ceramic itself. Another important phase that can form in this in an underwater environment is the hydrotalcite-like minerals. We call hydrotalcite-like because actually it's not just one type of mineral, but it's a class of material which are defined also as layer double hydroxide, LDH, that they form for the reaction of the amorphous phase present in the ceramic with the seawater. This type of reaction is similar to the reaction that occur into mortars, actually in cement. And the hydrotalcite is becoming, we are recognizing hydrotalcite in many ceramics from underwater sites. And yeah, they are very, very interesting mineral phases. They form, as you can see, plate crystals. They are like lamellae, and they normally develop into cavities, right? Because it's the way where they can mainly express. They can find a place where to develop, to crystallize, and to grow. In some cases, we recognize hydrotalcite also at the rim of porosity, but the pores were then filled by calcite. So this is the detail of this image, in which inside we have calcite and outside we have this darker rim form of hydrotalcite. Obviously, under the scanning electron microscope, we can see the chemistry, and we had to couple this with diffraction data. So diffraction data show us the same as before. We used two different set of samples, one from a land and the other one from underwater environment, same type of material, linked together. They have the same composition originally, but they experience different post-positional environments. We have hydrotalcite present only in the one from the underwater site. In the specific, this is a case study from southern Italy, from Puglia, and it is a cargo of amphora. Okay. Great. Let's see another aspect, which is very important, especially when we want to trace the provenance of a ceramic material. A ceramic material which experiences a long period underwater obviously can be enriched in some chemical elements, and some chemical elements can be depleted, can be leached. So this means that if you want to trace the provenance of a ceramic in a cargo, because we know very well that ceramic were used to transport goods, to transport wine, oil, fish sauces, or whatever, and we don't know from where a cargo was coming, from where the oil was coming, we need to make analysis of the ceramic base, but also of the chemical composition of the ceramic itself. So, but if the ceramic were, let's say, contaminated, is not the proper word, but the chemistry was changed, how can we know to compare them with a possible original one from a reference data set? We need to clean the data from the possible elements which were, let's say, enriched or leached. So they were depleted during the period of the ceramic experience underwater. Okay? So there are some chemical elements which are, let's say, they can easily be removed from a ceramic material because they form soluble cations, because they have a low ionic potential. And here there are some of them: sodium, potassium, rubidium, magnesium, calcium, strontium, barium, iron, but also some trace elements like cesium, lead, and manganese. Right. So if you want to see this, considering the ionic potential, we can have that these elements are those mainly represent represent normally hydrated and soluble cations, or soluble complex ions, okay, like the phosphorus and sulfurs. So other elements like titanium, zirconium are much more stable. These are collected here in the periodic table, the chemical periodic table. And according to the studies done in literature by different authors, the elements which mainly are enriched in marine environments are magnesium, calcium, iron, and manganese, while potassium, rubidium, barium, and cesium are the ones that tend to be depleted, are lost during the period the material experience underwater. They are leached. Great. How can we, but we know that the underwater environment can be very different from a place to another. The chemistry of the water is, let's say, similar around the world, but the chemistry of an archaeological deposit may be affected also by the other materials present in the site. So as we said, wood, we can have metals, we can have glass, we can have other elements, we can have stones, right? As well as the sediments in which the material lay down. So in order to understand the type of alteration our material underwent, the best would be to recognize the type of ceramic, for instance, a specific type of amphora or bowl or whatever, and to correlate that with the possible production area. Say, for instance, this Dressel 6 can come from Fasana, which was a production site in Croatia. To compare that with the production site and to see which are the chemical elements which change in relation to the post-depositional environment, right? So taking in this way two materials which come from the same production but experience different alteration environment allow us to determine which are the chemical elements which change over the time. But always it's not simple to do that, right? So a possibility is we thought how to face this problem and what to do. So the best, as I said, is to take a reference collection and make the comparison. A way to do that is to consider the chemical composition of your ceramic and to try to define which are the chemical elements which varied using a method as the one proposed by Boucher de Garrigos in 1999, in which you can study the variability of each chemical element in the complex of the data set you are analyzing. Okay? It's quite complex, but you can take a matrix of these elements and to see which are the elements much more variable inside the data set. Let's see what we have done. We took samples from an underwater site in Puglia at Torre Santa Sabina and made of this type of amphoras, which were produced locally in Apani and Giancola, two sites nearby in Puglia. We took also some samples from Apani and Giancola, and we made the comparison between the two types of amphoras. So it's actually the same type of amphora, but experience underwater post-depositional environment and the one which were still present in the production site inland. So the thing that was done was to determine which were the elements much more variable in the system. And I know that this type of diagram may be difficult to be read, but when the elements become along this line, which is asymptotic, and you see this is asymptotic behavior, they become, let's say, stable. while these elements here in the first part of the diagram are those characterized by a higher variability. Why they are highly valuable? Because probably they were enriched or depleted during the period experienced underwater. Obviously, we are actually comparing two sets of data, the original one and the one which were affected mainly by changes. All right. So this can be also expressed in terms of the variation that we see in elements, considering the average composition of the material coming from the production site and the one from underwater. So you take your samples from underwater, the average of each chemical element, and you divide that for the average of that chemical element from the sample from the land, from the production site. You normalize your data to the reference data, right? And when you see that the element is, let's say, close to 1, means that there is not much difference between the original one and the one from underwater. So the element is stable. While you have positive values, it means that that element was enriched. While negative values determine that there was a leaching. Okay? Great. Obviously, that somebody can tell me, okay, Lara, but I see that, for instance, there's enrichment in calcite. This means that calcium increases in quantity. And I can see that. But we have another problem that if I enrich something in an element, the average composition of all the other will change. Right? It's like you taking a cake and adding some chocolate. And then you measure the quantity of nutrients. It will change also the other ones. What is a method to solve this problem? Not to work with absolute values, but divide all the chemical elements by the element which has a lower variability. Transforming all the data into what we call log transform ratio. So we divide all the chemical element by the element which has the lowest variability and transform everything in logarithm-based step. Right? This is a way to solve the problem. And in this way, we experimented the data and we have seen, and in the example I reported you, that the sample which experience underwater environment, which are around the circle, overlap with those from the land, represented here by the blue crosses. So obviously somebody of you may tell me, okay, but the samples which experience underwater environment, they have quite a large variability with respect to the one that you see from the land. But this is also related to probably a little variation that we have also in the production of the ceramic itself, and or different period of production, because the production site didn't last only for one time, but it lasted for probably some decades. And also the clay use had an internal variability. So I know this is quite a complex topic, but it can be faced into this way. So I would like to thank you for the attention, and if you have questions, I'm here to try to answer.
Thank you, Lara. Thank you. Can you hear me? Yeah. Thank you for this very insightful and methodological approach to understanding submerged ceramic heritage. And our final speaker for today is Professor Silvestro Ruffolo from the University of Calabria. He will explore the biodeterioration of submerged cultural heritage, and he will present sustainable approaches to conservation in marine environments. Silvestro, please go ahead.
Yes, just a second. Okay. Okay. Can you hear me, first of all?
Yes, we can hear you and we can see your
Clearly?
screen.
Okay. And okay, perfect. I will go on. The last presentation will be a little bit more informative than the previous one, because I enjoyed the previous ones, because I like I like graphs and numbers and the analytical approach. But this I decided to do an less numbers and graphs and more more images. Okay, what I'm going to talk today is about the biodeterioration and conservation of submerged cult heritage. And when we talk about underwater cult heritage, we have to cite the UNESCO 2001 Convention on Protection of Cultural Heritage, because it was the first time that UNESCO, that is on a UN body, they made for the first time guidelines for the protection, exploitation of underwater cultural heritage. And if you want to talk about challenges that the issues about underwater cultural heritage, the first one should be the legal protection, because if you have a archaeological site, you can in a real environment, what you can do is to make a fence, to construct something to avoid an undesired intrusion. An underwater environment, it's quite difficult to do something like that. And the another issue is related to what? To the to operational protection, because this is sorry. Because sorry. This is because I'm here with restoration students. They are very good students. They say hello to you. But the problem is that they're very good in something which is related to air, not to the aerial environment. If they have to restore, an archaeological wall, they could handle this. But underwater, the situation is it's easy to understand. It is very different, and technologies are different, and tools are different. So it's very difficult sometimes to do something in underwater. And the other issue is the public awareness and access. Not, if you have an underwater cultural heritage, underwater site, for example, in Bahia, and you have to dive or you have to snorkel. It's not easy for everyone to get access to this kind of cultural heritage. It's very peculiar. Okay, and the big difference between because Professor Mazzoli mentioned the degradation of torn material, no? And they mentioned biological, physical, and biological, chemical, biological, physical degradation. And but here we are in the marine environment, so the situation is it's different. So we have to take, if we want to focus on the degradation of material in underwater environment, we have to focus on two factors: the abiotic factors and biotic factors. The abiotic factors has to do with something which is not living, for example, the temperature of water, salinity, pH, and waves, and so on. But if we take into account the biotic factors, we have to deal with what? With living elements, with microorganisms and organisms. Okay. And when we talk about degradation, we have to define what is degradation. And Professor Mazzoli already defined this term, but I want to tell it again. Degradation is defined as the set of processes that modify the physical, morphological, and aesthetic structure of an artifact on an archaeological site. And we refer to biodeterioration as the undesirable change in the properties of a material caused by the vital activity of organisms. And sometimes people use biodeterioration and biodegradation as synonymous, but they are not, because biodegradation is referred to if the substrate is organic material and this organic material is degraded by living organisms, then we have biodegradation. For example, if I have a protein that is degraded by a microorganism, we have biodegradation. Biodeterioration is the right term to be used for the impact, degradation, deterioration due by living organisms on materials. Okay. If we see something, we take a look of degradation, physical degradation, for example, in underwater environment. Degradation forms are different, but not so different from what happens in a real environment. So we can have exfoliation, erosion, lagoon, and also anthropic damages. For example, here you have a crack. Here, here have a crack, which is due. It is a consequence of the Bradisism. Here we are in Baia, which is an underwater Roman city in Baia, which is near Naples, and is an underwater environment because of the Bradisism, which is a geological phenomena due to volcanism. And so this is the whole city is about 5 meters in depth. Okay, but move on biological degradation. What happens to imagine to take a piece of marble, for example, cleaned, and put in underwater. Okay, what happens in just in few minutes after putting it into the water is that on the surface there is I will also observe an absorption of organic molecules on the surface. Okay, then what happens is that these kind of molecules can promote the adhesion of other organisms, and then this growing, this film is growing, and then what I have is a biofouling, which is a complex mixture of molecules, microorganisms, and also organisms. Okay. Okay. So when I deal with that so-called biodeterioration or biofouling, it's another term to describe this phenomena, I have two different types of biological colonization. And these two types are very different from a conservation point of view, because I can have a epilitic colonization, which is a biofilm, okay? Is a biofilm which it remains on the surface, okay? Is epilitic. And the second type is the endolytic colonization. In this case, what I can have is a very more complex and dangerous phenomena, which is we can have some pitting, holes produced by the microorganisms that can get into the storm materials. Okay. When I talk about epilitic damage, synonymous is bioincrustation. If I have an incrustation from a conservative point of view, it's not so dangerous, because I can, for example, I can remove this incrustation, and then the material is more or less cleaned. The concept of clean surface in underwater environment, it's quite different from cleaned that in regular environment, because it's not the level of cleaning, it's not so high. But we can say that, okay, I can clean a bioincrustated surface quite easily. It's very tough incrustation sometimes, but it's quite easy. Okay, but these are some microorganisms that can form bioincrustation. We can have bryozoas, foraminifera, and so on. Okay, so what I should do in this case? I have this incrustation. I can clean it with some tools that afterwards I will show you something about that, because sometimes you have to, since they are very tough incrustation, we have to use very tough tools. Okay. The other type that we refer to is the bioerosion. The bioerosion is given by endolytic organisms that can be microscopic or macroscopic, and they create tunnels, holes inside the materials. Okay. The material subjected to this kind of degradation is limestone, calcareous materials. Okay. Why? Because the mechanism, the mechanism involved in the creation of such holes in such erosion is related to the possibility of the microorganism to produce acids, and locally the acids can corrode the carbonatic materials, as just said before in the previous presentations. So for this reason, metals and ceramics are not subjected to endolytic degradation due to the absence of calcium carbonate. Lara Marital would say, no, it's not true. In the ceramics, there are some calcium carbonate. It's real, yeah, it's true. I mean, there are some. There is calcium carbonate also, maybe can be present in the ceramics, but it's not the main constituent. So this is the main point. This is the point. Okay. And this is a statue which is very, very interesting, because if you take a quick look here, you can see that here I have no endolytic attack, but here, yes. And this is a statue which is musealized in the castle, in the Museum of Baia. Okay. It is very interesting because it can show you something. Here I have not any colonization. Here I have nothing. The surface is quite in good condition. Here not. Why? Because it was buried to the sand till here, and here it was exposed to the water, and therefore to the endolytics. So the sand can protect against endolytic attack. And the biodegradation can completely change the artifact. Professor Mazzoli referred to recession rate. Here, we have a big recession rate. I mean, it's very difficult to modelize such degradation, but it's very important. Okay. Here there are some SEM images about how carbonatic substrate can appear under after endolytic attack. Here, the endolytic agent was Acleona chelata. Here there are some spicules of Acleona chelata, and these are the footprint, if you want to say, the footprint of the Acleona chelata. Okay, can make very severe damage. Here is a limestone with different level of endolytic attack. As you can see, I can have a very big degradation, very severe degradation. Okay, it's up to 70% of loss of material. Okay. A very interesting thing that we have observed. We have observed many biological degradation pattern on marble, and we observed that if I have a fine-grained marble, it's less prone to be attacked by endolytics if we compare to medium and coarse-grained. So the bigger is the grain size, the higher will be the endolytic attack. So it's a very interesting thing. The next step is, okay, this is we can recognize some bioincrustation, bioerosion, and so on. But what can I do? Because, here we are with my students of restoration, and then, okay, it's cool. I observed this kind of deterioration, but what can I do? Because I would like to conserve, to restore, to do something. Okay, and it's not easy, as I said before, because generally, when we deal with biological degradation, students, what can I use? They say biocides. They're yelling biocide. Okay, I use biocide in a real environment, and is it just a liquid? Is a liquid that I can apply on a surface, and I can kill the microorganism. Here in underwater environment, I cannot do that. No, because I cannot apply a liquid if I am in underwater. So the application of biocides, it's not possible. So what can I do? I can mechanically remove the incrustation, for example. I can use geotextile, and I will show you. I can cover to protect. Or, for example, I can use if I use some mortars to integrate something, I should use a mortar which is less prone to be attacked by degradation, by biofouling. Okay, or I can use something more. I can use a coating. It's not easy to do that, but we tried also to coat in some way stone materials in underwater environment. Cleaning test. When I clean, what I should do is to take some sample and see which are the components of the biofouling, and to check if there are some endolytic species. Because if there are endolytic species, I have to pay more attention to be because if I make a cleaning, if I clean today, within a certain period of time, I would have an endolytic attack, for example. Another interesting thing is the use of geotextile. Okay, is a sheet, okay, of plastic mostly, and I can cover, for example, if I have a mosaic made of carbonatic, the tesserae are tesserae have a carbonatic nature, what I can do is to cover, because if you, as I said before, if I isolate in the sand, for example, the material, it will be not attacked by endolytics. Okay, so if I cover, I isolate the surface from the environment, so I can protect the artifacts here. And of course, after a certain period of time, what happens is that the upper surface of the textile will be colonized. So it's a sacrifice. So when I want to show to visitors for example, the artifact, I to get off the geotextile, and then I can put it back. Okay. Ceramics, as I said before, it is subjected to epiphytic colonization, but not usually endolytic, okay, colonization. In a project, we tried to set up a sort of walks that can be applied directly in underwater environment. And then we tried to understand if this can be effective or not against biofouling. So we made some tests. That what we saw is that the colonization was there was a slowdown of colonization. So the main the main outcome of this project was, okay, you can slow down in some way the colonization, but you cannot avoid. Okay, you cannot. It's hard to avoid the colonization of a surface. But what can you do? It's to slow down. And here there are some papers that were written on this topic. Lastly, I would like to show you a project which was ended in 3 years ago, I think, or less. It was about an integrated more technology, a merge of more technologies to how to say for the conservation of underwater cat heritage. Okay, so we have chosen an underwater ecological site, Castelnuovo Marinella, in near Rome. And what we did is a characterization of storm materials and of incrustation and biofouling, and a team of engineers made some tools for do what? For underwater cleaning, because as I said before, the big problem sometimes is to clean the surface, physically clean. The only way to clean the surface is by mechanical cleaning. So we will need some drillers and similar to remove this the incrustations. So they tested some sort of drillers or something like this that can be used in underwater with some batteries, and then you can change the batteries directly in underwater. It's some tools that are very useful for underwater restorers. Another task was to understand, once I cleaned a surface, once I've cleaned a surface, I have to check with a semi-automatic way which is the speed of biofouling reform. So if I put a camera, for example, I can understand when I should clean again. Okay, so it's an algorithm, a is a tool which can be very useful for who is in charge for the maintenance of underwater site. And lastly, we tried to make some mortars, repair mortars that can be used underwater and that can have an anti-fouling effect. And then we tested in underwater environment. And again, the main outcome was I can slow down in some way the formation of biofilms, but it's not possible to avoid it. Okay, I'm finished. Sorry if I boring you.
No,
Thank
not
you.
at all. Not at all. Thank you very much, Professor Ruffolo, for that impactful presentation and the practical insights into biofouling the heritage protection. And before we close, I'd like to open the floor for questions from the audience. Of course, feel free to use the Q&A function or raise your hands. If you would like to address a specific speaker, I will grant you access to the microphone and your camera. Till you do that, we already have a question for Professor Mazzoli. So, Claudio, the question is from Mailin. Dear Professor Mazzoli, thanks for the presentation. I'm doing aging tests on calcitic marbles. I feel like in the ideal scenario, even if we synthesize all research studies, example on-site and lab measurements, it is possible perhaps to model down to a specific stone type, calcite marble, to be precise, but still would be a blanket quantitative model for, let's say, the whole carbonate rocks. So, Claudio?
Well, of course, it's not easy, but as much as you know the influence of the, can you hear me, yes?
Yes, we can hear you, but if you can also open your camera would be great. And also
Okay.
Professor Ruffolo as well.
Yeah, sure. Well, let's say, of course, it's not easy, but if you know what is, well, I think that at the end, what you have to do is, if you have a specific case study, for example, of a building with built with a specific material, at the end, you should also make specific experiments to see what is the behavior of that specific material in that environment. But if you are in a frame of a model which accounts for, in general, the effect of the petrographic features like grain size distribution, porosity, the color, the surface roughness, and the effect of the environmental parameters in terms of course, what you can get from the climate stations, but also in terms of surface temperature and the exposition of the stone to orientation of the stone. Then you can test on for a relatively short, like 1 year, the behavior of samples of that specific stone, just to tune the model to the specific stone material of interest, at least to see how precise is the model for that material. Okay.
Thank you, Claudio. I don't know if Maylin wants something to add on that, but I think you were very analytical towards this question. And of course, we can open the questions to the students that are following on site. So of course, you can ask them as you are there, and they can ask the questions either to you, Claudio, or to Professor Ruffolo, and vice versa.
And then Clara, and then Clara,
And Lara, of
obviously.
course, and Lara, yeah.
She's here.
No, I think you fully covered every aspect, both from informational side and from practical one. In any case, if you do not have any questions, either the people that are following online, yes, mailing, let me grant you position access to talk, and of course, you can open also your camera. Yeah, mailing, the floor is yours.
Okay, can you hear me?
Yes, we can hear you loud and clear.
Right, okay. Thank you, Professor Mazzoli, for the answer. As I am doing a kind of a climate change also review, also in terms of the biodeterioration that Professor Ruffalo was talking about. I do have a question for Professor Ruffalo about because when I was reading some literature, because I'm not a biologist in this field, but so I was reading the literature review, and well, they said especially for biodeterioration, it's quite the exact mechanisms, down to each specific biofilm, like bacteria or lichens. It's very understudied, so you cannot really know, the exact mechanism down to each type, and so it makes it difficult to, when it becomes like a biofilm, like interaction of communities, then it becomes really difficult to understand the exact mechanism the deterioration patterns are doing. And also, like in some literature, they say that some biofilms are beneficial for the sculpture, like for land-based, what I read. So in that case, would it be kind of better if we leave the biofilm as it is, like underwater, rather than removing it in some cases?
Yes, this is a good question, because if you understand that everything which is on the surface is apolitic, you can leave it. Yes, the answer is yes. The problem is if I leave everything, the readability of the artifact can be avoided. I mean, if I have a column, if I have a statue which is fully covered by an incrustation that not allow the readability of the surface, I cannot answer. I mean, from a conservation point of view, sometimes you are right. If everything is apolitic, I would leave the connellies right there, the biofilm is right there, and nothing happened on the surface of the artifact. So the first step is to understand what is going on. If everything is apolitic, we can choose to leave or remove. If there are endolytic colonization, it would be better to do something. Okay. But you are right. The community which is on the surface is very complex, and it's outside of our scope. For a biologist, pure biologist, it is very interesting. But yes, I think the workflow is like this: to understand apolitic, endolytic, and then choose to restore with who is in charge of the management of the site. That's what I think.
Thank you. I think you covered everything on that side. Do you have any other questions to address to our esteemed speakers? If this is not the case,
Just say one
yeah,
thing? Can I just
yeah,
say
Claudio,
one thing about
course.
this? Of course, yes, I agree with what Professor Ruffalo said. It's, of course, one issue is what is what we want to do with that, because of course some of the statues may be recovered and put in a museum, but then they are out of context. So the question is, do we want to leave everything underwater and build up an underwater museum? And so, of course, the approach is very different from just recovering a few things and putting them in a museum on land. So it's a different, also the type of view for the how to visit and how to enjoy, you know, these cultural heritage.
Mm-hmm. Thank you, Claudio. We have Professor Ruffalo.
Yes, what I didn't mention, but it's a solution. It's to put the copy in the underwater site. Okay, I can, as Professor Mazzoli said, I can bring the statue, put into the museum, but I can make a copy and put on the underwater site. That what sometimes it happens. Yes, I think it's a good solution.
Yeah, it's quite often done also on land, actually. So you may see a copy in a square where there is pollution and everything, but the original one is inside a museum and then preserved.
Thank you, Claudio. We have another question from Jem or Yem, I don't know, Erika Nick. Have there been any studies already that show the effects of marine pollution to the biodeterioration of submerged cultural heritage objects? I don't know if anyone of you may reply on that.
Sometimes, I don't know. We didn't study the effect of pollution actually on the biodeterioration, but sometimes it will slow down the biodeterioration is maybe because if the pollution is so high that the microorganism can be affected by this kind of pollution and will be less prone to attack the surface. This is what I read sometimes, but I didn't do that. This kind of research actually.
Claudio, you have to add anything on that?
Well, we actually missed most of the answer because we had connection problems, but yes, actually there is a colleague of mine here, which is also involved in THETIDA, is Luigi Germinario, who made experiments on the effects of both biodeterioration and acidification on the deterioration of carbonate stones underwater, putting samples at Ischia, where you have CO2 vents, which lower water pH, so simulating future effects of ocean acidification. And well, he's writing some papers about this. And so, well, just follow his publications to see his interesting results.
Thank you, Claudio. Do you have any other questions from the audience? If no, I would like to thank you all for your participation and of course our wonderful speakers, Claudio, Lara, Silvestro, for generously sharing your knowledge, very precious to everyone and each one of us. And this, of course, concludes the third webinar, the third THETIDA webinar. We were very happy to be here, and of course, stay tuned. for our next episode, which will continue to build on this conversation, bringing together disciplines, technologies, and communities to protect our coastal and underwater heritage in a changing climate. And for you that are wondering about the recording of this webinar, you will be able to find it on our website and of course on our YouTube channel. Do not forget to follow us on the social media. We even have a TikTok account. Please register and follow us there on our Instagram account, LinkedIn account, Facebook account, and of course register to our YouTube channel. So thank you everyone, and until next time, take care. Bye bye.
Bye bye. Thank you.